All right, everybody, so today we're going to do some R practice, but it turns out the example in the notes is an example that I've talked about before, so we're going to open with this little snippet from my TED Talk. If you remember that first decade of the web, it was really a static place. You could go online, you could look at pages, and they were put up either by organizations who had teams to do it, or by individuals who were really tech savvy for the time. And with the rise of social media and social networks in the early 2000s, the web was completely changed to a place where now the vast majority of content we interact with is put up by average users, either in YouTube videos or blog posts or product reviews or social media postings. And it's also become a much more interactive place where people are interacting with others, they're commenting, they're sharing, they're not just reading. So Facebook's not the only place you can do this, but it's the biggest, and it serves to illustrate the numbers. Facebook has 1.2 billion users per month. So half the Earth's internet population is using Facebook. They're a site, along with others, that's allowed people to create an online persona with very little technical skill. And people responded by putting huge amounts of personal data online. So the result is that we have behavioral, preference, demographic data for hundreds of millions of people, which is unprecedented in history. And as a computer scientist, what this means is that I've been able to build models that can predict all sorts of hidden attributes for all of you that you don't even know you're sharing information about. As scientists, we use that to help the way people interact online, but there's less altruistic applications. And there's a problem in that users don't really understand these techniques and how they work, and even if they did, they don't have a lot of control over it. So what I want to talk to you about today is some of these things that we're able to do, and then give us some ideas of how we might go forward to move some control back into the hands of users. So this is Target the company. I didn't just put that logo on this poor pregnant woman's belly. You may have seen this anecdote that was printed in Forbes magazine where Target sent a flyer to this 15-year-old girl with advertisements and coupons for baby bottles and diapers and cribs 2 weeks before she told her parents that she was pregnant. Yeah, the dad was really upset. So how did Target figure out that this high school girl was pregnant before she told her parents? It turns out that they have the purchase history for hundreds of thousands of customers, and they compute what they call a pregnancy score, which is not just whether or not a woman's pregnant, but what her due date is. And they compute that not by looking at like the obvious things like she's buying a crib or baby clothes, but things like she bought more vitamins than she normally had, or she bought a handbag that's big enough to hold diapers. And by themselves, those purchases don't seem like they might reveal a lot, but it's a pattern of behavior that when you take it in the context of thousands of other people, starts to actually reveal some insights. So that's the kind of thing that we do when we're predicting stuff about you on social media. We're looking for little patterns of behavior that when you detect them among millions of people, lets us find out all kinds of things. So the example from the notes actually originates from this post on Reddit, where a man is saying, you know, my wife's Fitbit has been showing her heartbeat consistently high for the last couple days. Is there a way we can recalibrate it? And someone responds, has she experienced anything stressful? Is she maybe pregnant? And the guy says, she could be pregnant. And then he finds out that she is pregnant, and there's a whole bunch of edits following up where everybody's surprised, and he did a whole bunch of media about this, that essentially they found out she was pregnant because of what was here on the Reddit page, looking at the Fitbit. And so the reason that Target looks at pregnancy and that this might be interesting is because most people don't change their shopping habits. You buy the same thing at the same stores all the time. But when you have a baby, because you suddenly have to start buying new things, it's one of those times in life where people are very susceptible to changing their habits, which makes them really attractive for companies. So the question becomes, can you actually tell that someone is pregnant because their heart rate goes up on their Fitbit? And if you can, Fitbit has this really valuable piece of information all of a sudden that they can work with and potentially sell to people. So that's the question. Can we tell if someone's pregnant by an increased heart rate on the Fitbit? Okay, so let's see if we actually can figure this out. This is our practice problem. You can download this from the lecture notes for today. And what you can see is that we've taken data of the resting heart rates for 15 pregnant women. This is our data here. And we know that non-pregnant women have a mean resting heart rate of 73 with a standard deviation of 15. So what we want to do is figure out, is the mean for this group, our pregnant women, significantly different than the mean for women who are not pregnant? That's what we want to check. Now, we haven't done this before, and so we're going to do a little bit of new material to help us learn some things in R. So what we're going to learn is the z-test statistic. So if you remember, we learned the z-score. We take the observed value minus the known mean and divide it by the standard deviation. Now, intuitively, that's going to give us how many standard deviations above or below the mean our observed value is. So just want to do one quick example to kind of push that home. So imagine that we have an observed value of 10, and our mean is 20, and our standard deviation is 10. Now, since our mean is 10, and our observed value is 10, and our mean is 20, the observed value is 10 below the mean. Now, the standard deviation is 10, right? And we're 10 below the mean. And hey, if you do this, you get -1, right? 10 minus 20 is -10. Divided by 10 is 1. And that's exactly right. If we're 10 below the mean, we're 1 standard deviation below the mean. So that's what the z-score gives us. How many standard deviations above or below the mean are we? Okay, so the problem that we have to practice on is to compare this sample of 15 pregnant women to the known heart rate for non-pregnant women. And we want to see, is our sample representative of or different from the known population? And to do that, we do something similar to the z-scores. We're going to compute the z-test statistic, which is a lot like the z-scores that we just looked at. The formula is very similar, but it requires one thing that we haven't done so far, and that's this measure called the standard error of the mean. This is essentially the standard deviation of the mean when you have multiple samples. We compute this by taking the standard deviation of the known population and dividing it by the square root of the number of samples that we have. And that gives us this thing called the standard error. To compute the z-score for the sample versus the population, which is going to tell us the probability that the sample is the same as our known population, we take this value, m, which is essentially the mean of our sample, and we subtract the mean for our known population. We divide that by the standard error, and that gives us this z statistic. Now that looks a lot like the z-score that we computed before, right? Instead of dividing by the standard deviation, we're dividing by the standard error. We have the mean in both cases, and here we have the mean for the population instead of a specific observation. Essentially, we've transformed this z-score that we used for a single observation into a z-score that we can use for a sample population versus a known population. So we've converted a single observation to the mean for our sample population. We've converted our standard deviation to the standard error. And that's it. This is going to give us a score that we're going to plug in, and then we come over to this table of standard normal probabilities and we look up our z-score to get a p-value. Okay, so first, how do we use this table? You have z-scores over here and they have 1 decimal place, so like 2.6 or 2.5. The values across the top here are the second decimal place. So if our score, for example, were -3.41, we would go to the row for -3.4 and then over here to get the 1, and that would give us our value. If it were -3.07, we'd come to the -3.0 row and then over to 7, and that would give us our value. So let's actually run this with the data that we have in the practice problem to try it out. Okay, so here we are in R, and the first thing we want to do is put in our data that we have for our known pregnant women. Now, how do we do that? We haven't actually put in data before, we've only loaded it up. So here's a new R thing for you. We're going to create a variable called P for pregnant women, and we want to store the list of values that we have there. So to create a list or a vector, you use this command C, which you may have seen if you've been watching other tutorials. C lets you create a list, and inside you just put in all your numbers. So I'm going to type in all the ones that we have in the sample problem. Okay, and with the speed of video, I have those all typed. I hit enter, and now P, we can see over here, has my whole list of numbers in it. So those are the known values for our sample, we also know that the mean for non-pregnant women, so let's call that NP mean, is 73, and the non-pregnant standard deviation is 15. Now you don't need to store those in variables, but I'm doing it just to make things a little bit easier. Okay, so now we have to compute the standard error. So we're going to call that SE, and if you remember, SE is the standard deviation, so we have that stored here, divided by the square root of the number of observations that we have. So we've got our list here in C, but instead of counting all of them, we can use this command length of P, and that'll count them for us. And just to show you those, length of P tells us that there's 15 things there. So SE, you can now see, is storing the standard deviation 15 divided by the square root of 15, which is 3.87. All right, so now that we have the standard error, we can compute the z-test statistic. And to do that, it's the same as the z-score, except we're going to use the mean of our sample population instead of the observation. So we'll call it ztest for the z-test statistic. And that's going to be equal to the mean for our sample, so the mean for P, minus the known mean divided by the standard error, SE. And there you can see now we have our z-test statistic of 1.84. So that means the same thing as our z-scores did, that the pregnant population that we have sampled here is 1.84 standard deviations above the mean for their heart rate. And now we can go back to that table we were looking at, and we can look up 1.84. So here we go down to 1.8, and we're going to go over from 0, 1, 2, 3, 4. And what this gives us is the p-value. In this case, it's the probability that our sample mean is different from the population mean. You could flip this around to say that there's a 3.3-ish% chance that our sample mean is the same as the population mean. Now, we tend to look for 5% as our threshold for p-values. So that would be, if we're looking at the big numbers, 95%, or if we're looking at the small numbers, 5%. And if we can say that there's a 95% chance that our sample mean is different, or a 5% chance that the sample mean is the same, then we conclude that they're probably different. And so in this case, because our value here is over 0.95, we say that we assume that our sample of pregnant women with their pulse rates from Fitbit is significantly different than the resting heart rate of non-pregnant women. Okay, so that should help you work through the first exercise, but now we're going to switch and just do a little bit more practice in R. What I have loaded up here is the Facebook data that's linked on the course website. You can see all of it spread out here, and I'm going to export this as a CSV. So I'm going to be able to open it, and I'll call it facebook.csv. Now we're going to switch back over to R, and I want to load that file up. So if you remember, we can do read.csv, file.choose, and header equals true. This will let me pick it. And now there's all of our data. If I want to store that, I have to put it in a variable. So I'm going to do FB arrow and then read that file. Okay, so now we can see our Facebook data here, and remember in RStudio you can click on it and you can actually see a preview. So I'm going to make that a little smaller, but I'll keep it open. Okay, so let's look at some commands that we might want to know. We might want to see all the variable names in our table. So we could do names of, let's try that again, names of Facebook, FB, and now here's all the variable names. So there's a lot of columns in there with these big, long, complicated variable names, but we can see what all of them are. All right, so let's work with this data a little bit. We're going to select some of the columns from here. I've pulled a few of them for us. So let's create a variable fb2 that we're going to set equal to, and now we're going to select columns, and we do that by saying the original variable name, and then in square brackets, normally you would do this where you put a list of rows, comma, a list of columns, which we've seen before. I'm not going to list any rows, I want to select them all, so I leave that blank and then just put a comma, and then I'm going to list the columns that I want. To do that, I actually need to do a list, which remember we do with C, and that doesn't stand for columns, that's just C is the command for a list. And then I'm going to put the columns that I want. So I'm going to do 2, 4, 8, 61, 62, and 63. Now that data is in FB2, and if I click it here, you see it is 6 variables, and we have a shorter list of things here. Okay, if I wanted to get rid of variables that are blank, I can do that too. So I could make fb3 equals, and then this new command, na.omit, which means get rid of the things that are blank. So I'm going to omit all of the blanks from fb2. And now you can see fb3 has 382 observations, so it's gotten rid of blanks because there were 437. Now I might want to change some things up. So I have 6 variables, that's 6 columns, and I want to rename those to be a little more user-friendly than what we have here. So to do that, I can say the names for FB3 are now going to be equal to this new list of names that I'm going to give. Again, if I make a list, I have to use that C value, and I'm going to give the list. So the first one will be gender, that's for this column. The second one we'll call year, for what year in school are you. The third, international. The fourth, how much time have you spent? We'll call that average per day. And then if we scroll over, the next column is how many times per day. And finally, how many friends do you have? Okay, so I have 6 new variable names here. And when I put that in, now I get new names. If I click on FB3, now we can see my names are actually up there. So now we have a much nicer way to refer to things. Now we can do some computations like we haven't been able to do before because we haven't learned those commands. Let's say we want to know the total number of friends based on gender. So the average total number of friends by gender. So what's the average for women and what's the average for men? There's a command called tapply, or you could call it tapply, I suppose. And what we want to give are our variables. So we're going to do fb3 $ total friends, which is what we want summarized. We want it summarized by gender, and we want the mean. And so that shows us for gender 1, the mean is 431. For gender 2, the mean is 436. And so this allows you to summarize your first variable grouped by your second variable, and here you can give the statistic. So we could do the same thing with the standard deviation, and now you see we get the standard deviation for each group. Another thing that we can do is to create subsets of this data based on a particular value. So for example, we could say S3, which will just make our subset, is equal to, and then we use the command subset of fb3 $year, and we'll make that less than or equal to 4. Oh, sorry, I have a typo there. Let's try it again. Subset. So first we give the table name, then we give the variable name, And now we have S3 here. We have 285 observations. What is done is select everything out of FB3 where the year was less than or equal to 4. So now I have a subset of the data. We could do that for any of these variables. Let's do one other one just to kind of see a difference. We could say S2 is equal to a subset of FB3 where the year variable is, and we just want to give a list. So maybe we want to look at people in their second or their fourth year. To do that, we can say in, which is an R command, which just means it includes the value. And then we give a list, and again, a list always has a C, 2, 4. And now we can see here's S2, we have 160 observations. And if we click on it, if we scroll a little bit, we can see that the years are always 2s or 4. So our year is in the set 2 and 4. So that's how we do subsets. Okay, so I want to talk a little bit about how to create an R script, which is basically a little script that you can load up that has a bunch of commands that you might want to do multiple times. So for example, we've been computing z-scores, and for those we have an observed value, let's use that OB, let's say that's equal to 7. We have to know the mean, let's say that's 5, and the standard deviation, which we'll say is 6. And to compute the z-score, we use the observed value minus the mean divided by the standard deviation, and we get the answer. But there's not a command to just do the z-score in R. If we try that, it's empty. So what we're going to do is define a function called z-score that will do this command for us so we don't have to type it out every time. So to do that, we're going to come to a plain text editor. I'm going to start with a comment. This isn't functional code. This is just so I know what's going on. And now we know what we want to do, right? We want to take the observed value minus the mean divided by the standard deviation. And these are variable names that I just made up. And what we do to make a function is that we name the function, so we'll call it z-score. And then we use the word function. And in parentheses, we put the names of the variables that we want to use inside the function. So I'm going to pass in some values, just like we've done with things in R like mean or median or names, right? You're passing in some values. These are just the names I'm going to use inside the code here to refer to those values. So the observed, the mean, and the standard deviation. And I'm actually going to compute those values here. Now I could just copy and paste this code into R to test it out. So I do that, and now I can do z-score and then just pass in some values. Let's say our observed value is 50, the mean is 30, the standard deviation is 19. It gives us our answer. Now, instead of having to define that every time, I can save this script as zscore.r, and we'll put that in this week's folder. And then I can load that up into R so I have access to it. So let's go back to R. We're going to remove z-score. So now if I tried that command, it won't work. I have to redefine it. And now what I want to do is load up my script. So to do that, you just use the command source. That's what you use to load up a script. You can either put the path or do file.choose like we've been doing. Pick our script here. And that's it. Now we have it defined. So if we go back and try to run the z-score, it works again. And we can use that for any number of values that we want. So scripts are a way that you can write code that you know you're going to use a bunch of times. They can be really long and have lots of functions or data loading commands or plotting commands. And it allows you to just load it up and have all those commands accessible. So there you go. That's how you create a script in R and how to load it back up. And that's it for our R tutorial for today. Here's your class activity to try out. Using that data that we just loaded up, how many international students are there, how many domestic students, and then try to find the best measure of central tendency broken down by international versus domestic for minutes per day spent on Facebook, time per day spent checking Facebook, and total Facebook friends. Those measures may differ between the two groups because one may have, for example, a long tail that distorts the mean and one might not. So check all of that out. And if you're really feeling ambitious, try a plot or two And now you're ready with R, once you have all of this mastered, to move on to the more sophisticated hypothesis testing that we'll try next week.